So this video will describe several methods of numerical integration. So the problem is that we have a definite integral like this, where we integrate this function of x from the limits a to b. And that's being shown here. Here's our function, and here are the limits a to b, and this definite integral is interpreted as the area under this curve. So what we want to do to solve this numerically is to change this from an integral to a sum of discrete points, and that will also introduce a bit of error. And so the procedure is to partition the interval from a to b using n points, and that will be done by selecting a delta x, a spacing between these points. And a convenient way to pick this spacing is to take the b minus a, which is this distance, divided by n minus 1, and that will give us delta x. So there's delta x, and we're going to partition this interval into points like that. So So there are the points, the x values, and there are the y values of the function at those particular points. So what we'll do is evaluate the function at these different values of x, and there's an example of the function evaluated x2. And those values will be these values here. And we'll take each one of these functions evaluated at these discrete values of x, we'll multiply by this term, which is a weighting function, and then we'll add them up. And that will be the essence of this numerical integration technique. We'll have three different techniques, and one of the ways to distinguish between them is some of them will be so-called closed methods, and those will require that we evaluate the function at the endpoint. So we'll have to be able to calculate that point and or that point. Open methods of integration do not use this point or this point. So the open methods, as it'll turn out, will be more versatile for integrating functions that may be singular. They may go to infinity at the limits. So if that happens, we can't use a closed method because we wouldn't be able to evaluate the function at this point or this point. Closed methods will not be suitable for calculating functions that go to infinity, but they will be good for other functions or for data. Okay, so the way we're going to develop these methods of numerical integration is to locally approximate the function using some simple function that we can integrate. So the function that we want to integrate is this black function here, and these are the points that we've selected when we partitioned the interval. And what we're going to do is to take three of these points and develop a function that will apply locally and approximate the black function. And so the simplest way of doing that is to say that the approximating function is just equal to this value at the midpoint. So if p is our approximating function over this interval from this point to that point, then a simple way to approximate the black line is to just say it equals the function at x2. So basically what we would be saying now is that the area under the curve here shown in pink would be equal to, or at least be approximating, the area under the curve, the black curve. So another way of doing this would be to approximate the black function with a linear function that goes from this point to that point, in which case the approximating function would be this one. And perhaps a better way would be to approximate it using a quadratic function that looks like this. that would allow us to have a function that approximates the black function that has some curvature to it. And you can see this pink function, or this pink area, probably would be a better approximation of the area under the black curve. These three different approximating functions will form the basis for the different numerical integration techniques. So the first one is called the midpoint method, and it uses this method of approximation that's just assuming that we can use this intermediate value to approximate the function between these points. So the procedure is to say that the area under the curve from x1 to x3 is obtained by integrating this approximate function. And so since the approximate function is just simply the function at x2, we can substitute that in there, and we can then do this integral, and we get this result. So the area under the curve is just x3 minus x2, which is that width, times f at x2, which is that height. So we get the area under the curve as this rectangle. That's fairly straightforward. Okay, so to use this, we have to extend it to what's called the composite method. And that'll be done by going from one rectangle here to multiple rectangles. So we can extend this procedure onto an interval that's been partitioned into many, using many points. So first we would consider two intervals. This would be the first one that we just calculated on the previous page. And then the next one would be done using this formula here. So this rectangle would be calculated there, the area of that rectangle, and the area of that rectangle would be calculated there. If we added another interval, this third one here, we would add another term here, f at x6, which is that point, times x7 minus x5, which is that minus that. So I think you can see the pattern emerging where the area under the curve where we would have many rectangles would be the sum of f evaluated at x sub I times the difference between x at I plus 1 minus x at I minus 1. And in this case, we're summing over the points that start at I equals 2 and then go every other point up to the n minus 1 point. So in order for this to work, we have to have the number of points that are odd. If we have an even number of points, then we would say end right here, and we wouldn't have a complete rectangle. So that's a restriction on the method. And you can see here that the method requires that we calculate f of x at these red points. None of these points are the f of x at the limits, so we don't need to calculate that point, nor do we need to know that point. So this is an open method of integration, and we could use it to integrate functions that were singular at this point or this point. So what I'd like to do is show you how this method that we started with is manifested in this composite method. Wait, I think we skipped a slide. Let me first go to this slide. A variation on the midpoint method is that we just saw is the forward and backward rectangle method, and this uses the same shape of element, a rectangle, but it evaluates the function at all the points except for one. So the forward rectangle method, where n equals 7, would be given by this expression, and that would require that for I equals 1, we evaluate the function here at this point and then multiply by that distance, so we would get that rectangle. And then for I equals 2, we have that rectangle, and so on. So we have to use the function evaluated at all these red points, not that point, and we get the areas of these 5 rectangles that we would add up. We can also conceive of doing this in sort of a backwards way, where we evaluate the function at this point and multiply by this distance to get this area. And so what we're saying is that this area approximates the function here. And then we can add up these rectangles that are calculated in this way. This would be a backwards rectangle method. And so these are similar to the midpoint method in that they use rectangles, but they're a little more general because they can use any number of points, whereas the midpoint method that we just saw could only use an odd number of points. But they're also a little more restrictive because we have to be able to evaluate the function f of x at one of the endpoints, at either this endpoint or at that endpoint, depending upon which method we're using. Okay, so now we're going to go backwards and take a look at this general function that we started with. And I want to show you how it's manifested in these methods that we've just seen. So what we said we were going to do is determine a definite integral by coming up with a function evaluated at discrete points times a weighting function, and then we would add up those terms as a summation. Okay, so we've seen a center difference, the forward and backward rectangle different methods, and they're copied here. So what we're saying is that we're evaluating the function here at these different values of I, so at these different locations. And the weighting function in this case is given here by xi plus 1 minus x minus 1, I minus 1. So for each value of the function that we're using, we're weighting it based on the delta x value. And similarly, there's the weighting function for forward. It's also delta x, but it's a little bit different, xi plus 1 minus xi. And then for backwards difference, we also have this as which we can interpret as a weighting function shown here. So this gives you an idea, I think, of what we mean by this general approach. We're evaluating the function at certain points, and then we're weighting it, in this case using values of the spacing along the x-axis. Okay, so let's take a look at the trapezoid method. This is using a linear function to interpolate the function we're interested in over these 3 points. So what we're saying is the pink area would represent and approximate the area under the black curve between these 3 points. So to calculate the area, we integrate this function p of x from x1 to x3. There's p of x. We go and we do this integral here, and then we can also get expressions for the slope and the intercept. And when we do that, we go through a little bit of algebra, and we get that the area of the curve is equal to this expression. And this is the function at x3 plus x1 divided by 2. So that's the average between that function and that function. So we would have, so this term right here is the average. It's going to be equal to that guy. And then this is the delta x between this point and that point. Okay, so that's the area underneath this curve for that particular geometric entity, that pink entity. So we can also do a composite trapezoid method by having basically repeating what we just did. So here are 5 different geometric entities for integrating this function from this point to that point. And we would do the first 3 of these using this formula here, which would be the area of that polygon, and this formula here would give us that area, and this one would give us that area. It looks like these numbers are offset a little bit, but I think you can understand that this number corresponds to that point. So what we can do is we see things repeating. So we have these terms here, and when we go to this next one, we increment each one of these terms by 1. And so what we can get is the general formula in terms of a summation. Instead of writing it out discretely like this, we can write it as a general summation where we are now summing from I equals 1 to n minus 1, and we are summing every one. So I equals 1 and 2 and 3. And then we're calculating in a term for I equals 1, and then we're adding it to a term for I equals 2, and so on. We're doing that up to n minus 1. And then we go and we divide all of that by 1/2. And the 1/2 is just simply this 1/2 here. We could put it in here, and each time that we calculate these values of f of x, we could divide it in half, but it's probably easier to just factor it out. So that's the composite trapezoid method. Now the last method that we'll look at will extend this approach and interpolate the function between these 3 points using a quadratic. So we're just adding this x squared term here in this interpolating function. That'll allow the interpolating function to have some curvature to it, which will probably make it fit this curve, the actual curve between these points, a little bit better. So the procedure for developing Simpson's method is similar, where we're going to integrate the approximating function from x1 to x3. There's the approximating function, and when we do this integral, we get this term from integrating this term, this one from integrating this linear term, and this one from integrating this constant. And so what we need to do is to evaluate this these set of terms from x1 to x3. So when we do that, after a little bit of algebra, we get that the area shown here is equal to this, x3 minus x1 over 6 times this term in brackets plus 4 times this term plus this term in brackets. So what we can do to simplify this down is, if we say that the spacing between these points here is even, so delta x is the same over the whole interval. If that's true, then this guy here we recognize as this, and this guy here will also be the approximating function. And if that's the case, if delta x is indeed constant, then we can recognize this as f, the function evaluated at x1. This guy would be the function evaluated at x1 plus x3 divided by 2, which would be just x2. And this will be f of x evaluated at x3. Okay? So we end up with a formula for the area under this curve equal to this. Delta x is constant, so we'll know what it is. We take that, divide by 6, and we come up with, and the function evaluated at x1 plus 4 times function evaluated at x2 plus the function evaluated at x3. And actually, the way this will work is that this is what you get if the function is, actually what will turn out is this 6 will turn into a 3, because this x3 minus x2, if we say that's delta x there, from one point there to that point, then this actually will be 2 delta x. So that should be delta x over 3. So the composite method is shown here. That should be delta x over 3, where we have this polygon, or it's actually this geometric entity, because this is a curve now, is approximated by this function, or this term here. This one is this term, and this one is this term. So what we can do is use this to infer what the summation should be. And basically, we're going to be adding this term and this term and this term. And the way we can write that is that the total area is equal to the summation of this grouping, f at xi times 4 f at xi plus 1 times, or plus f at x I plus 2. And in this case, I starts at 1, and then it jumps to 3 and 5 and so on. So I is only going to be including odd numbers of points. And this is done up to n minus 2 number of points. So we would do, so in this case, we would have, this guy would be over here, we would have 7 points. And we would do this for I equals 1, I equals 3, and I equals 5, because n minus 2 is 5, and so that would be the last point that we would use. So essentially what we've done is taken this set of terms here and written it as a summation. So this and this would be equivalent if we used n equal to 7. And if we fix that typo there, where that should be 3. Okay, so that's the Simpson method. One of the downsides is that it requires an odd number of points. So that puts a restriction on us, and it also requires that we have a uniform delta x. So the spacing between these points here is uniform. It also uses the value of f of x at the limits. So it's a closed method. Okay, so here's the summary of the methods that we've seen. These are the summations, and basically what we're doing here is evaluating the function at different locations, and we're weighting that with some kind of way of determining a delta x, and then we're adding it up. And we're doing this in various different ways. Okay, in this way, we're just removing the delta x, because delta x is constant. And here we're really just adding up the function evaluated at different locations. So this method, the midpoint method, it's open. It requires odd number of points, and it'll work for any delta x. The trapezoid is closed method, any number of points and any delta x. And so because of this, it's good for integrating data, because when we want to integrate data, we're going to know the value at the endpoints. We may have an odd number or an even number of points, but the trapezoid method doesn't really matter. And the value of delta x may vary. but the trapezoid method allows for this. The Simpson method, it's closed, it requires an odd number of points and a uniform delta x, and it will be good for integrating functions that are not singular at the endpoints of the integration. If it is singular, then you need to use a method that's open, like the midpoint method. Okay, so those are the various different methods for numerical integration that we'll look at. What I'd like you to do now is to try out this method by doing the example that's available in an electronic form with this video. It's also available in the in your notes. And what this is going to involve is to solve this integral here. Integrate the square root of x dx from 0 to 4. So we'll want to partition this interval using 5 points, and the points will be evenly spaced, so we can calculate delta x this way. What you should do is calculate the values for the different methods, and this table is set up so that you can calculate the terms, the individual terms in the series here, and then you'll add those terms up to do the summation and calculate the integral. We also should figure out what this integral is exactly and write it there, and then determine the relative error down here at the bottom. So you'll evaluate, this should be the numerical value of the integral, and this should give you the relative error of using that approximate value and that exact value. Okay, so do this exercise and then start the next video, and we'll go over this exercise.